the homework. Believe it was 15, 16, 17. Yeah. All right. So there was a couple things in there. 15 said, find the components perpendicular to the slope. Is that what it said? Yeah, parallel and perpendicular to the slope. Yep. So probably another case of where I probably should have read this before we gave it to you so we could chat about it a little bit, but I think you persisted. Well, some of you persisted through it, so that's good. So perpendicular to the slope would be here, right? And parallel to the slope would be here. So that's what they wanted. What I should have told you was, hey, you can move the coordinates anywhere you want. Like they don't have, the rectangular coordinates don't have to be horizontal and vertical. They can be at any position that you want them, right? We normally draw it horizontal and vertical, X, Y. That's the rectangular Cartesian coordinate system. But what I'm saying now is, hey, this can get rotated X and Y anywhere you want it. And it actually is helpful, especially on slope problems. This is a slope problem. When we get into friction, we'll do this all the time. So that's what they wanted you to do. Perpendicular to the slope, parallel to the slope, find the components. So that means, okay, we have to draw components in a new position, right? A little bit different. They do add up to the 800. So X and Y just becomes a new X and a new Y. This is Fx, this is Fy. The tricky part is trying to find the angle within the triangle, right? You're given an angle, so that's got to move up there somehow. The way I think about it is in this position, right? Perpendicular, horizontal, right? As we rotate this, whatever angle the red is on, the green is on to vertical, right? They move through the same angle. So that means if it's 30 here, it's 30 there. If you kind of draw it graphically accurate, then that helps too, because that looks like 30. This does not look like 30. So once you had that, like those two pieces, oh, we're moving the coordinate system. We're still finding rectangular coordinates. They're just not horizontal and vertical. They are perpendicular, parallel to the slope. Then I could go after, since I know that angle, opposite side would be sine. And that's going to equal opposite. That is Fx over 800. And then the other one is cosine 30 Fy over 800. Make sense? You persisted through it? Yeah, so if I just don't answer emails, sometimes you figure it out yourself, right? I was a little busy yesterday. Yeah, Ben. So I like that you've moved up closer. Love it. But I can hear you now because there's no fan.
You could have heard me otherwise without the fan from back then.
Not really. I have a hard of hearing. I'm old, man.
So this assignment was due like by today, 8 a.m., right?
Yeah. But honestly, you probably have picked up by now. I don't really care. As long as you do it. Like it's helpful if you do it before I do it, right? So really, what works best is if you struggle with it. Yeah. Like Amy, for example, she struggled with it, right? And I didn't answer her question, which I didn't do that intentionally, but that's actually a good process, right? If you struggle with the material and then I come in and clean it up, you think I'm great. I'm not. You're great because you struggled with it first, and then I just gave you the clues to figure it out. So anyway, go ahead.
I struggled with both 17 and 16, so I didn't even finish them.
Okay, it's fine. So as I'm going through it, finish it in a different color. So instead of a pencil, just finish it in red pen or red pencil or something different.
Number 16, there's like this tow truck and some sort of weird angle like that.
Okay. We'll get there. Let's do 15 first, Ben. Focus. Does anyone smell bacon now? Now I'm really freaking out because I feel like I smell bacon. Oh, okay, good. I thought maybe now they got the ducting like coming in from some restaurant or something. Like, that's just rude. Damn, that smells good. Just saying. All right, next time, Timothy, you gotta bring it up for everybody. No, not a thing. We can all bring our own food. All right,
But this just making myself extra work, like I extended my
Ah.
life down.
you could do that. I mean, you didn't know to put it on the surface like I did, but you know, as long as you got the coordinates parallel and perpendicular, it worked out, right? Yeah. I mean, I didn't run the number. Anybody get a number on this? What do we get for FX? Why negative? Is it pointing? Where? No. Where's positive X? Oh, okay. Okay. So here's positive X, right? So that would make this direction negative X. Which way does this go? Negative. It's definitely negative. So when you build these components, you got to build them tip to tail. And the only way to do that is here. Now you could also, I mean, you could go here and here, but the directions are going to be the same. They got to go together tip to tail. So yeah, it actually is a negative. I get 400. Is that right? Okay. And so the other thing you could write is, because there is no negative forces in this class, there's only forces at a negative direction. So that is a force at a negative direction. You could also say 400 pounds downhill. That'd be fine too. So a negative force, what would that be? Anyone know what a negative force actually is? Vacuum. That's exactly right. That is a negative force, is a vacuum. So in statics, we only have forces at a negative direction. It's not a negative force. Anyway. And then the other one is 800 times 30 cosine. 692.82. And that is plus or minus. Pounds. And it's also minus. Well, that's a typo. What is it, 15? Have you all found the answers in the back of the book? Yeah, students are usually pretty good at that stuff. So I try to toss in. 215 says FY negative 693. And FX negative 400. Go away sound. So yeah, I have FY and FX. It might be the way they wrote it, with A being and then B, I don't know. But I do have X and Y.
Snapshot did not include the other triangle.
Oh, it didn't include that? Really? I took a picture of the whole page. Sorry. Sorry. Did you find a book on Google or something?
Somebody had a picture problem.
Yeah, I'm pretty sure you can find everything on Google.
I also just turned one back into the library.
The book?
That one.
No, I finally have one checked out. It should be good.
Perfect.
Am I the only one who read it online?
I did. I didn't like them. Like the ebook?
Yeah.
What do you mean?
Oh, yeah.
I mean, at the very
Don't worry.
bottom of like the chapter, stuff like that, if there's like problems, that's where I get my stuff.
It's generational, Ben. Don't worry about it. I love a book in my hands. Just look better carrying a book when you're walking around, you know. Yeah, you can't download it. Yeah. right?
That you, like, always have internet.
And that you always have service, right? Yep. All right, what's this mean?
Does that have the rectangular component already set up? Like how we did the.
It kind of does, yeah. Anyone else have an idea what this means?
No,
I don't get it.
Yeah, so it's giving you the slope, but it's giving it to you in rise and run. So it's giving you a triangle, a 3, 4, 5 triangle. But even if you didn't know 3, 4, 5, like if you want that angle and you know that and that, how could you get that angle? Yeah, so tangent, I'll call it theta, is 3/4. So theta equals tangent minus 1, 3/4. Right? So this is a common notation in the civil engineering world and in the land development world, in the construction world, and it's just giving you rise and run, giving you slope of something. So I tend to take the rise and run and just turn it into an angle and then work it normally. You can do ratios. In other words, the 150 relates to the 3 because they're both vertical. And then an X component would relate to the 4, so you can set up these ratios. I don't like to teach that because I've already taught trigonometry. We'll just stay with that, right? So if you want to explore the whole ratio thing, go for it. But I take 3 and 4 and switch it into an angle. So that angle is 36.8698. And then from that, then I can just go for the same process of setting up the coordinates or the components. Right? This is our X. This is our FY, and that angle is the same as that angle. So again, once you get that set up, then it's just trig again to figure out FY and FX. This is going to be the cosine. This is opposite. That's going to be the sine. So it becomes sine of 36.8698 equals FX over 150. So FX equals, I'm going to hit enter. So I have an extra one. What is it? Sine. 90. Is it pounds on the second one?
Yeah.
Okay. And then the FY is going to be cosine, same thing, cosine FY over 150. So I'm not going to write that one out again. Run out of space. There's my angle, cosine 150 times 120. And the FX is pointing down the hill, so we could give it a negative. And the FY is pointing into the hill. That would be a negative direction also. You could also just put a vector pointing left and a vector pointing down. That's appropriate too. So however you want to keep track of directions, right? We need that when we go to add things up. So however you keep track of it, that's fine. Plus and minus works really good because then you just write them out, right? Pluses interact with minuses and yeah. Good. Question. It's okay. All right. Ben's tow truck. Pretty sure it's a tow truck, right? Some kind of boom truck. There it is. I didn't draw all the truck, just enough, right? And they wanted to know what? Vertical and horizontal. So first task needs to be to draw it. So vertical is going to be vertical. And this has down effect. So this is going to come down, right? And this has left effect. It's pulling to the left some. So that means the X is going to come over. So there's the FY and FX. And so the coordinate system is back in the normal position where this is minus X and this is plus Y. Okay, so then it's just digging out an angle and trying to figure out like what do we have? Where are the angles and how do we get them into our triangle so we can solve something? Ideas? How'd you do it?
Did the 50 degrees.
You did the 50 degrees
Oh,
somewhere, right? I know where, but
the opposite of 40.
yeah, so maybe looking at this triangle here. No. Because this, if this is 40 and this is 90, that's what? Sure. But you're just working your way around, right? Yeah, because now I know this is 90 and this is 50, so this has to be 40. Which then this is 90, this has to be 50. Yep. Yeah, you just start digging them out, right? You start moving things around, trying to follow the rules, not breaking any rules, noticing where the 90s are because they're going to help you. Once you get the internal angles and you know the hypotenuse, then you're good to go on fx and fy. If I use the 40, I can use sine. So sine 40 equals fx over 1,000 pounds. Right? It's opposite the 40 for x. So it's sine 40. So fx equals 642.79. And that's pounds, and that's heading in the negative x direction or that way. And then the other one would be if I use the same angle, it's going to be cosine. I could use the sine of 50, right? But I'll just stick with the same way we did it before, using the same angle. It's going to be fy over 1,000 pounds. 40 cosine 766. Vertically downward. It's good, Ben? Is that how you did it? Kinda. Yeah. Excellent.
Oh, no, sorry.
Was a blurry. There we go. Good. So draw the picture. That's super helpful. Got to draw the picture. All right, 17 gave you some vectors kind of in word type problem, right? Said you have 80 kips. What's a kip again? 1,000 pounds. So we're talking big numbers when you see kips. I have 80 kips kind of down and to the left, I think it said, right? At a 20-degree angle from vertical. So again, just try to draw that in. And then I wanted the rectangle components. Is that right? So again, we have down effect and we have left effect. So this is going to be Fy, going to be Fx. So if I go for X first, sine, because it's opposite, 20 equals Fx over 80K. Fx equals 2736. And that looks to be negative or to the left. And then cosine 20, Fy over 80K, Fy equals 7518. And that is down, also negative. Questions? we've beat this thing to death. Beat it with a stick. Trig functions. What?
To say kilometers, but that we can't.
Case kips,
I wanna make sure.
kilometers would be km, yeah,
There's nothing else. it's
Yep.
just K.
nope. And you have to, I mean, we do have to, in our head shift, like if we have a US problem, K is definitely not gonna be kilometers, right? It's gonna be something in the US. It's gonna be
It's-
kips,
I think it's
common,
US.
yep. 1,000 pounds, pounds is US, yep. Question, Ben? No? Okay. Do I need to do this one? You got it. I think we're good. We've beat this to death. KN, what is that? Kilo newtons. So newtons are also load. And then kilo, metric system puts all this, the prescripts on. Kilo, mega, giga, all could be newtons, right? So Newton is like a pound. About 4.48 difference between a Newton and a pound, so. Yeah. This one I'll draw it. We don't need to calculate it. It would be up and over. This would be positive, this would be negative. All right, turn them in. Excellent. We are moving on to chapter 3. So exciting. I can tell you're all just, yeah, let's do that. Let's move on. Let's do something different. There's some coming back to you too, if you want to pick them up. So chapter 3 starts with resultants of concurrent force systems, which we've actually kind of already done. Well, I mean, we have all the technique for it, and we've actually done it a couple times in class, but not like in homework. So the first 2 problems I gave you are just finding the resultant of a concurrent force system. What is a concurrent force system? How would you like to, you're at a party Saturday night, you're hanging out with people and you really want to tell them like what a concurrent force system is. How'd you explain that to somebody that's not in this class? Because they really want to hear about it. Yeah, that's it. That is it. All the forces come from the same point, or their lines of action can intersect. So I could put one out here like this. I drew my line off just a little bit, but the point is all their lines of action could intersect if I could draw a better angle, right? So that's the little bit of the tricky part. These are obviously concurrent, 1, 2, 3, definitely concurrent. But this one, if its line of action did go through that point, remember the principle of transmissibility allows us to move it to that point. Boom, we have a concurrent force system. So the opposite of that would be the standard beam problem, where we might have a couple supports, we might have a load down, we might have a load at an angle. Clearly, even if you extended all of their lines of action, they're not going to intersect, right? So we have concurrent and non-concurrent. So this chapter finds the resultants of concurrent force systems and non-concurrent. This we pretty much have done. What's the method that we could use to do this? To find the resultant, the single force that could replace those 4.
The X5 forces for all of them.
Yep. Find the components of each force, X and Y, add them all up. When you do that, F1, F2, F3, F4, we're gonna end up with the summation of the forces in the X, and that's gonna be F1X plus F2X plus F. Actually, it would be minus F3X minus F4X. Did I get those right? F1 is positive? Right, because if we're thinking just in the X, F1 is positive. What's F2?
Oh, it just.
In the X, yeah, F2 is 0, so I could just go, okay, that's 0. What about F3, positive or negative? Definitely, the X component is negative, and F4 has a negative X component, right? All that is going to give us the resultant X component. Then, of course, we do the same thing. Some forces in the Y. F1 is actually 0. I'll just write it in. We have a minus F2X, or oops, Y. We have a minus F3Y. And then F4 is positive or negative in the Y. I have one positive, one negative. We need someone to break the tie. F4, the Y component, does it have up effect? Yeah, it has up effect. Up is positive. Right, and all that equals the component in the Y direction of the resultant. And that these are all just trig, right? Just build the triangle, figure it out. Build the triangle, figure it out. Once we have our Rx and our Ry, we can then draw those. And I'm going to guess here that the Y is going down. This is a guess. And what do you think on the X? It depends on how big that is, but we'll say it goes this way.
So when you're drawing it out and you're trying to keep it to scale, the starting point of F4 is separated.
Correct.
So do we only include the length of the starting point to the end point?
So,
and we don't include
yeah, so if the problem was like this, right, and maybe there was a big block here or something, right? That's how that ended up out there. When I would draw the force system, I just move F4 right here, and I just put it right here.
So we can
And then
treat
I'd
it
go to
like
work.
it's
Yep.
attached, and
Yep.
We
You
don't
can
have
just
to,
move it right to the point,
I guess in most cases it'll tell you.
draw the force, the system, and then go for it. Yeah. Yep. Once I have this, then I can say, oh, okay, this is a known, that's a known. I can come up with R. That's the resultant, the single force that could replace all 4 of these forces. Take it out, put this one in. Now I can go to strength of materials and understand what's going on. If I have 10 forces on a system, I don't know the overall effect. I can't look at it and go, oh, I know what's going on. I have to go through this process to come up with that single force. Now I know what this thing feels, and I can kind of design for that. Good? Perfect. Now we need to know how to oh, here's 4 forces, not concurrent, so it's called non-concurrent. Pretty clever. But how do I come up with a single force? And where is it on the object? Right? So we need new methods here. These are the methods for concurrent. We've done it. That was the whole chapter. The first part of chapter 3 just does it some more, so you'll just practice it. But now we need to understand how to do this. The difference is these forces are a distance apart. These forces all go through the same point. So none of these forces, I'll call this point A. On a concurrent system, none of these forces are trying to rotate that point. They go right through the point. Okay? It's like taking a door and taking your finger and pushing directly on the hinge. What's it do to the door? Nothing. It's not how you open a door. You'll create no rotation if you just push on the hinge. And you can take as many forces as you want and push on that hinge and the door still doesn't move, right? So in a concurrent system, there is no rotational effect. The only thing these forces are trying to do is move point A to the right or move point A up or down or move point A left. Translation, that's all it's doing. Right? And we do have to design for that. Like we don't want things to move right and left and up and down, but we also don't want things to rotate. These, all of these, if I look at point A, what's this trying to do to point A? Rotate it. If point A stayed put, there was nothing else going on and just a force here, this thing would take off and rotate. If point A was a free pin or free to rotate. That makes sense? What's this one trying to do? Yeah, also rotate, but and translate, both. What's this one trying to do? Rotate, trying to rotate. No matter what point you pick, if you pick point B or point C or point D, the other forces are trying to rotate about that point. What's this force trying to do about that point? It's pointing up, so it's trying to do what? Trying to move it up. Is it trying to rotate it, or is it like my finger on the door hinge? It's trying to push it, translation. Is it trying to rotate point A? Absolutely not. It's like your finger pushing on the door hinge. It's not doing a thing. What about this force about point B? Trying to translate it, but there's no rotation there. That makes sense? I mean, if you don't believe me, just get up, walk over to the door and do this to the hinge and see what happens to the door. It just doesn't move, right? So if the force goes through the point, there's no rotation, right? We just talked about that here. Are any of these forces trying to rotate about point A? No, they're going straight through the point. No rotation. This is important because this is how we solve these. We have to understand what's creating rotation and what's fighting rotation, right? Our goal, next chapter is equilibrium, but our goal is like, there is no resultant. Like we just found a resultant, but what we want out of our force systems is no resultant. That means the building is not rotating. If you have a leftover rotation that's not opposed by anything, it's going to rotate. Like if I push on this hard enough, it's going to rotate. Nothing's opposing that, right? So we need to build systems that like oppose the forces. So we're going to get to where we want. Hey, we don't want any of these leftover resultants. We want them all to go away. All right. That's good. Now let's talk about how we kind of do it. So I'm going to start with a basic beam. Oh, look at that. The red came through. I don't want to waste paper. I'll just use it. So step one is just to understand that we do want a resultant, and these early systems are going to have resultants. I want to be able to calculate them. So I'll put in 100 pounds, and then I'll put in, we'll go with another 50 pounds, and then I'll just put another one in. 60 pounds. So concurrent or non-concurrent? Definitely non-concurrent. They are not going through the same spot. It's a parallel system, which is the simplest system. That's what we start with. And I'm going to say this is 5 feet and this is 10 feet. So what you do need to know is like how far apart the forces are and what angles they're on, right? So I just made them all vertical. That's the easiest form of understanding what's going on. So the way we do this is we essentially have to collect all of the rotational effects about a spot, a point. It can't be just a lot of points, it's just one spot. So when we pick those up, of course, we're gonna have to label points. So it can be A, B, or C. It can be anywhere. It could even be like, it's D, something like that. It can be anywhere. So at some point, you're gonna just choose the spot. I think in the beginning, the book says, hey, do it here at point A, right? But it'll be up to you at some point. If they give you a beam and they don't give you the thickness of the beam, which is very common in the book, then we just neglect the thickness. It's like a thin line thing, okay? So even though I might draw this down here, the point of application is there, here, and here. Remember, we do have transmissibility. This could actually be drawn up there, and then everything's in line. So just don't have heartburn over the thickness of the beam because they'll not give it to you most of the time. Just ignore that. All right, so what we have to do is, in order to find the resultant, we do a couple things. We have to collect all the translational effects first. So we did that last chapter. That's the up and down and the side to side. That's not rotation, right? So up and down, side to side. What do we have in the X direction for forces? It's not a trick question. It's a super easy question. There are none. So we have no X effect in this force system, right? So that's the other thing is, when we do these, we're looking at one force system, just a possible force system in time, right? It's not going to be all the force systems on it. It's just a snapshot of some force system. Okay. So what about the Y effect? Do we have Y forces? Yeah. So we need to go, okay, I need to sum those Y forces up. What are they? Yep. 100 pounds, which way is it going? Down. What about the 50? And the, right? And that's going to be our RY. Kind of just like concurrent, same kind of thing. If we had a force at an angle, we don't, we're parallel. But if we had a force at an angle, we'd have to find that Y component, right? And add it into this RY. And then we'd have an X also, but we don't have any X's in this system. We're going to keep it simple. So what's RY equal to? Anyone got that number? Oh yeah, I just added them all up, didn't I? That's why we work in teams right there. Anyone else get -90? Somebody else got -90, I'm sure. All right. So, yeah, so if we had like another force in here, I'm gonna highlight it in, and maybe it's 200, and it's at 50 degrees. So if that was in there also, right? Just another force, but this time at an angle. When we're summing up the Y effect, the vertical effect, what would we have to do? We'd have to find the Fy, that little creature, which is going to be sine 50, right, times 200, and add it into this, because that's part of the Y effect. And then we'd have to say, oh, crud, now there's an X effect. So now we got to come up with Rx, right? It just gets a little more complicated. So I'm going to just go parallel in the beginning. I think your homework's parallel in the beginning. And we'll just get rid of this little complication here. In reality, we have a lot of up and down forces, and we have a lot of side-to-side forces, and we have very few angled forces. Wind can generate an angled force. We have that. And then, of course, cable systems, they have lots of angles going on. But most of the time, we're a lot of vertical. All right, so we've collected that. There is no X. So the resultant force so like if the question said, what's the resultant force? And I don't care where it is, it's 90 pounds. It's the addition of all the forces up and down, right? If it's a parallel system. If it was an angled system, then you'd have to do X and Y, just like we did before, Pythagorean theorem to come up with R, okay?
We need to calculate the rotation because of-
Yeah, so there's more than just translation though. In a non-concurrent, we're not done. In a non-concurrent system, there's rotation. We have to account for the rotation. So the way we do that is called moments. And I really don't know the origin of that. Like, why do we call it moments? I have no idea, but it is torque. So if you know what torque is, that's a moment. It is a rotational effect. The units of moments are foot-pounds or Newton meters or inch pounds. All of those are just fine. Notice it's not foot per pound. It's not foot divided by pounds. It's a foot pound. It's feet times pounds. That's the unit of torque. So if you've ever torqued anything, like with a torque wrench on a bolt or anything, those are inch pounds. Okay, that's the rotational force that gets applied to a system. So what happens is these things are creating a rotation about different points. And moments are always about a single point, and it has to be chosen for you to know what the moment is. The moment equation is force times distance, super easy. And I write perpendicular distance. I put a little perpendicular in there because it's the force times the perpendicular distance to the point. So let's try to clarify that. This is the simplest system. So these are vertical. Where's perpendicular to vertical? Horizontal, right? And our distances are horizontal distances. So this is super simple in that we just see forces and distances, and they're perpendicular to each other. So if I wanted to know how much the 50 rotates about point A, all I do is I take the force. What's the force? 50. What's the distance perpendicular from this line of action to this point? 10 feet. Pretty simple. So I'd write that the moment of the 50 about point A, a lot of times you'll see it. The moment about point A of the 50, right? Because I need the point. I got to know where I'm doing the moment and what force I'm working with. Is going to be 50 pounds times 10 feet equals 500 foot-pounds, feet times pounds, foot-pounds. Right? That's the rotational effect of that single force about the point. That's what it's trying to do to it, is just like rotate. We will, yeah, but we need to talk about a sign convention because we need a new sign convention. When we did translation up and down, right and left of a force, what was our sign convention? How did we know plus and minus? Yeah, which way it points? What's this one? It's negative. What's this one? What's this one? Positive. That's translation, right? Now we have rotation. Oh, rotation's different. Rotation is like, what is this 50 trying to do about point A? So what I do is I kind of continue it at an arc to understand what it's trying to, how it's trying to rotate about point A. And you got to have the point, because guess what? About point C, it's different. It's trying to rotate the other direction, right? But I did it about point A. So that means I need to do my rotation in respect to point A. Is this clockwise or counterclockwise? Clockwise is negative. That's the rule. So clockwise is negative. Counterclockwise is positive for our torques or moments. So the 500 is negative about point A, and I always tag it with a little symbol. So that is a collected rotational effect. Right? And what we have to do is we have to pick a point and collect all the rotations. So we picked point A, I did. We found the moment of A, the 50. What's the moment of the 60 about point A? Still about point A, but this time is of the 60-pound force. 60 pounds times what's our distance? 15 feet, excellent. And that number is, oh, calculator's off. That doesn't help. Somebody said 900. Yep. Unit is foot-pounds. And the rotation is, careful, draw the arrow. Follow the arrow. This is like a bow and arrow. If you let go of it, tie a string onto this thing, it goes like this around point A. Correct? Is that clockwise or counterclockwise? Counterclockwise, this is positive, and it is counterclockwise. Those two moments are fighting each other, right? That's a good thing. We want opposing moments. Everything's going the same way. The whole system is just spinning off into outer space, and that's not great. Okay, so we have one more, the 100. What's the torque? What's the moment of the 100 about point A? Because I'm doing it A. I don't change my spot. I stay there.
It's just like pushing on the hinge.
It's pushing on the hinge. Is there any rotation? No. If I wrote it, what would it be? It would be 100 pounds times 0. Yeah, that's why there's no rotation. So it's 0. There is no rotation. So after I collect my moments, I just add them because now they are all at point A. So then my sum of the moments is equal to, and this is at point A, minus 500 foot-pounds plus 900 foot-pounds equals what?
400.
All right. Excellent. Excellent work. Everyone good with that? It's not too difficult. It is parallel. That's helpful. We're not done. We're not done. We're just getting there. We have the complicated part to come here. That's pretty simple. Collecting the moments is usually not too difficult. Just take your time. Get all the moments at one spot. Now that we have all the moments at one spot, this is the scenario. I can't really show you this anymore, but just like concurrent, our goal is to get rid of all the forces and just put one force on, the resultant. And I know the resultant. It's that magnitude, 90, because I just added up all those X's and Y's and came up with R, right? So 90 is my resultant. Here's my beam again. Here's my point A. And which way did 90 go? Negative. So which way is that? Down. Thank you. And where'd I do my moment at? A. So that's where I place it. I put my 90 pounds at A. The 90 pounds is the translational effect. We summed our moments, and what did we get for our sum? 400, and I think it was positive, right? So I also put that at A because that is at A. And I do it with that rotational hook because it's a rotational effect. It's not a translational effect. So now at A, I have my resultant translation of 90, and I have my rotation effect. I have them both there. That makes sense? That's what this beam's feeling. It's feeling a rotation of 400 and it's feeling a down effect of 90. Okay. And what I need to know is the 90 is not here. The 90 pounds is not at A, the rotation's at A. The 90 pounds is really out here somewhere. Or it's actually out here somewhere. It doesn't have to be on the object. That's super weird, just saying. I get it. That's kind of weird, but the resultant does not have to be on the object. The resultant is the resultant effect of the forces, right? These are the actual forces that are on the object. But we're trying to get rid of those and just understand, hey, what's the effect? And the effect is this, 90 down and a rotation of this of 400. So how do we know how far this is and whether it's here or here? It could also be here. Our moment tells us. We have to make that rotational effect with our 90 pounds. The equation is moment equals force times distance. Do we know the moment? Yep. Do we know the force? Yep. Do we know the distance? No. So we solve this for distance and say, oh, it's the moment divided by the force, which is 400 foot-pounds divided by what? 90 pounds, leaving feet. $490 divide 4 point, lots of fours, feet. That's how far away it is. But I need to create that rotation. Right? My force. So if I put it here pointing down, does it create that rotation? No, looks like it opposes it. And in this case, I need to create it. I need to have that same rotation. So it's not up there. Nope. Nope. It is the magnitude that we need, 90, but it could be here, 90, going up at 4.44 feet. So that would be, if you want it on the object, it would have to be there. Is that rotation the same as that? Yeah. So we created that rotation. So this, go ahead.
X is the point. The distance.
Yeah, X is this distance. Remember, it's always, this is always perpendicular to the force. The force is here. We do know it's vertical, right? So this is the other spot. It could be 90. 4.44 feet, right? Because that does create that effect also. Right? Yeah. So when we're doing non-concurrent systems, we want to come up with the resultant and where is it on the structure or off the structure? Just where is that effect? That's important to us. That was a lot. Did good. It's going to be more complicated when you do it all by yourself. You're going to be like, what did we do? How did we do that? Really, moments is the big thing. Like that's the new twist is we're understanding. Oh, get it? Twist. That was pretty good. We're that rotational effect, right? We're just collecting it. So X's, Y's, and rotation. Let's see here. Let's just do one out of the book.
So that one, you would say that the moment was point A. We were doing that for the moment at point A.
We chose it.
Okay. but
You can choose anywhere.
So in order to do a full analysis, would you have to do it at every point?
Nope. This is a full analysis. Pick one spot, collect the effects. X effect, Y effect, and rotational effect. Collect it at point A. That's what we did here. And then distribute the load out onto the structure.
I gotta find out later why we chose point A and we didn't have to do it around point B.
Nope. There is no rhyme or reason. There are easier points and harder points that are more difficult. But any point should work and give you the same exact solution.
But if I'm looking at the system that we were gonna do with 150 and the 60.
Yeah.
Just looking at those points.
Yep.
I feel like point B would be the one that would, like, if we had this beam. and
Yep.
All of those forces were acting on
Yep.
it. It looks like it would rotate, probably not equally, but it would rotate around point B, because we have on the left going down, on the right going up.
Yeah, so you have 100 and you have 60. 100's gonna have more rotation than the 60, correct?
Yeah.
The thing is, you're still gonna add up all the forces, even at point B, you're gonna add up all the forces and get 90. Right? So our resultant is the same. Now you're gonna add the 100 times 10 to get that rotation, the 60 times 5 to get that rotation, and those are gonna add up to a moment. It's not gonna be 400. It'll be something different, but then when you divide by your new moment divided by the 90, it'll give you the distance to the same exact spot as you just calculated. You'll end up with 90 at the same exact spot. It'll be a different division because it's a different length from there.
So when we got to the end with the 4.44,
Yep,
we were moving point A.
you are not, point A stays put, you are moving the 90.
The downward force.
Yep,
Okay,
it popped out here.
okay.
Yep, so once you move it, then you get rid of it there, and now you have just a beam and a force. And that is the same effect as this creature. Let's do another one. We'll pick one out of the book. Chapter 3. I'm hesitant to flop in there a angled force, so we're not doing that yet. We're not gonna do a symmetrical one. Let's do 29. You want to break first, or you're good? Let's kind of get a break, just drawing it, right? So a moment of silence while we all draw 29. So 29 looks like this if you don't have it. 29, this creature. Whoa.
The picture is above. the-
Yeah. Yeah. So the number of the problem is below the diagram. Trust me, you'll do the wrong problem.
That took me a long time just for. 15.
I'll do the wrong problem, yeah. Yep, so 29 is this creature. So. They do say locate the resultant with respect to point A. Which means do your moments at A, because then you'll find the resultant with respect to point A. Right, you'll find the perpendicular distance from that. So I'll give you a bit of time to draw the picture. And then I'll draw the picture, but you can start working on it before me, and then I'll trail behind on the overhead, and we'll see what we do. And the goal is to find the resultant and where it is from point A.
But with the triangle and circle, that platforms.
Yeah, it's a good question. What are these? Yeah, these are chapter 4. That's the supports. Yeah. So right now, we're finding like resultants of the force system. So these 3 forces, there's a resultant to that, right? And we're finding it. But in the end, we want the resultant to go away, and the supports, they resist the forces. So when we add in the supports next chapter, then the resultant goes away. And the system has no resultant force, which is good. We want the building to have no resultant force. That means it's just sitting here. So we'll get there. It's just the supports. We ignore them for now.
Is there, for what, the chapter 4 question, is there like a difference between structural
Yep.
like, integrity of the shapes?
Yep, absolutely. The triangle is a knife edge or a pin. We use triangle for both of those. Most time it's a free pin, meaning free to rotate, right? And the roller can only hold in the Y direction. It can't hold in the X. Expansion, thermal expansion. So we put thermal expansion joints in everything and connections. So if it heats up, it can expand. If it cools down, it can roll. All right, you got the drawing? Can I move the book? It's 4 kips, 4 feet, 5 kips, 3 feet, 2 kips, 2 feet. I'll draw it and then you'll see what I draw. Where are we doing our moments? At A. We are collecting everything at A. So I'm going to show you just another graphical way of thinking about this. Right? Take all the forces, move it to point A. It's essentially what we're doing when we add them all up, right? But I can't just move forces. That's not legal. But I can move them as long as I bring their moment with them, their rotational effect about the point where you're moving it. So if I'm going to move 4K over to here, then I need that moment effect, which is what? 4 times 7 is 4 times 7? 28. Is it kip feet? Yeah.
Forces in a straight line, you have to apply the opposite.
In order to move forces, you have to take their rotation with them. In order to move the 4K to here, I have to take the moment, which is 4K times 7, with it. Right? So I can write it the way we wrote it before, which is the moment about point A of the 4K is equal to what? It's 4K times 7 feet, which is 28 kip feet. Right? So graphically, you can draw it like this, like, oh, I moved the 4 over here. I got to bring the rotation with it. Now I want to move the 5 over. Moment about A of the 5K equals 5K times what? 3 feet. Moving it to here, 3 feet, that's 15 kip feet, and its rotation is this way. And I can draw those rotations up here if that's helpful. You have to remember where our position is. We are at A. Right? So that 15, that also comes in here. So if I move the 5K over, I got to bring the 15. If I'm going to move the 2K over to A, I've got to bring its rotation with it.
Why is it negative 28 kb?
Good question. What's the negative mean? Means the rotation is clockwise of the 4K. So here's 4K. How is that thing rotating about point A? I draw these in to this day. I draw them in when I do a problem, especially like when I did the support lubrication trucks. I had, close to 80 forces on that truck bed. Oh, I had a lot of rotation going on. So in order to get that kind of clear, you need a nice big picture and you need to understand the rotations about the point, whatever point you chose. So I don't know if this graphical helps, right? But since you chose A, everything moves there. Everything brings its rotation with it, and then you just can add it all up. Again, parallel systems are easiest because now I can just add forces. I don't have to do any Pythagorean theorem. I don't have an X and a Y. It's going to get there, but I just don't have that yet. So what's R equal? R is the magnitude of the resultant, the translation up and down. We got 4 up, 5 down, 2 down. 3K down. That's the magnitude of the resultant. That resultant is not at point A. It's somewhere out on the beam. Right? So what's the resultant of the moment? From the magnitudes of the forces. Right? 7 down, 4 up, left over 3K down.
But
No.
you just added small numbers of 2, 5, and 4, but what about?
No, not the small numbers. What are those called? No. What are these? They're forces. We added the vertical forces. 2K, 5K, 4K, and we got 3K down. We're not done. One step at a time. Right? That's what's next, though, is we add up the moments because they're all at point A, right? So what is the summation of our moments at A? Here they are, right? Negative 17 kip feet. Anyone else get that? Of the what? I don't have 3 kips anywhere. I have 2, 5, and 4. That's this. Is that rotation? No. Downforce. So -2, -5, plus 4 gives me a -3K or a force down.
Why would it be?
Because it's pointing down. Yeah, don't forget the translation is just which way it's pointing. Yep. It's gonna be a common thing for a while until you really get clear. Translation is just up and down. That's just points down, it's negative, points up, it's positive. Rotation has this crazy new sign convention. So yeah, it's just -28 and -4 is -32 plus 15 takes it back to negative 17. And the negative, what's that mean? It just means it's clockwise. That means the rotation of the sum of the moments is clockwise, and that's what we have to create, is this clockwise rotation. Okay, so now I can again draw my beam, because things are clearing up. Draw my point A. I know now that my resultant coming down at 3K, is it going to be to the right of A or to the left of A? If I have to make that rotation,
To the right.
it's got to be to the right. No question, it's got to be over here. It's a down force, it's got to be over there because that creates what kind of rotation? The same rotation as the sum of the moment. Yep. And I know the magnitude of this thing. What is it? 3K. I just don't know the distance. I know which side of A it is. I don't know how far. How do I get how far? Use the formula. Moment equals force times distance. Distance equals moment divided by force. My total moment is minus 17 kip feet divided by the force of minus 3 kips. It's going to give me just a distance, not plus or minus, but just gives you a distance. .66.
So it's gonna be it'll be 16.98, right? Because you multiply it by 3.
Whoa. Where are you multiplying by 3?
Well, if you go back to the formula.
No. Right here's the formula. We got 3K down. We don't know the distance. And we know the moment is 17. The sum of the moment is 17. Right? Okay, so then we just take the moment divided by the resultant. 17 divided by 3.
Is it correct to think of moment as torque?
Yeah, absolutely.
Moment is just.
Us engineers just call it moment. Go into an auto shop, they're gonna call it torque and then say, what the hell's a moment? What are you talking about? Like, why are you talking about that? Yeah.
Is there a reason we don't just call it torque?
Historically, I don't know why moment became a moment. Tom McCormick would know if you know Tom, if you got concrete. No, don't go momentum. No. It is just a torque. We call it a moment. And we have for ever. It's just not a recent thing.
Yeah.
I'm gonna look it up.
Yeah, no, there's probably some historical reason why we call it a moment, but it is torque. Same thing.
So-
Engineers like to be different. I don't know. Whatever. Go ahead.
So what I was thinking is, since we got the distance, it's 5.66, I was thinking we can go back to the moments, equal to force multiplied by distance.
Right.
I was like, oh, we should multiply 3K times 5.66.
And you're gonna get what? 17. You're right back to the moment that we found about point A.
Oh,
Yeah, it's just right back to this. So you're just running this back through this to get this, which is this, right? So, yeah,
So if this was like a real life situation.
it is.
It is. What we're trying to find is the force that point A is experiencing.
Yep. What it feels, not point A necessarily, but the whole beam.
If we're doing the whole beam, I mean, we have. the
Remember, we
support.
started at this, right? But we're not doing the supports yet. That would be too much information at once for a student.
Right.
It would be like, this is like a lot. We just did a lot. And so we don't want to add supports in yet to this
But because
chaos.
It's probably not actually moving. Right.
Absolutely not. We don't want it to move. So,
It's just-
yeah,
It's just the force
Right.
at that point is.
yep.
experiencing.
So what you're finding what you're finding is these three forces create an effect on the beam. That's what you're finding. These two supports fight that effect. If we've done this right and everything goes to zero. That's what we want, right? But we're just not ready to calculate these in yet. We got to understand, just understanding what we just did is huge. Like if you get this, like, hey, we can move forces around as long as we bring the rotation with it. We need that. That's golden. Then we can just, right. So what happens with the supports is we'll add those vectors in, but they're unknowns. Right now you're working with everything's known. We know the forces, right? 2, 5, 4. We know their distances. It's a good life. We have all knowns. When we get to the supports, these are going to become 2 vectors unknown, 3 vectors known. How do we find them? Right? And it's just a little more complicated. It's the same process, but it's algebra.
Oh, before you were with the textbook, I saw there's a problem below with 3 fourths, I think it is. Number 30.
Yeah, there's just 3 wheels and in loading conditions. Yeah, no supports there. The support's the ground. Yeah. Yep. But you can see kind of where we're heading, right? We're going to get into distributed loads and try to understand how they work. Then, we get into this kind of thing like, oh, there's a bunch of angled forces now and some supports, like what's going on here, right? And the point is we want to be able to calculate what's the load on the pin, what's the load on the roller, because then I can design those. Like, oh, we need a pin that can hold 14 kips. Like, that's a lot of load. That's a big pin. So that's kind of where we're heading.
Strength materials.
No, that's still statics. So now I know I need a pin that can carry 15 kips. I learned that from statics. But how big does the pin have to be? That's strength of materials. And what's the pin going to be made out of? You can make it out of steel or titanium or copper, or what are you going to make it out of? If it's copper, it's got to be this big. If it's steel, it's got to be this big. If it's titanium, it can be this big, right? But how do we calculate that? That's strength of materials. So I think it's good to put the whole problem together, and I'll do that a couple times in this class. And you'll be like, what the F is he doing? That's not statics, but it's good to see like why are we doing this? And it's so we can design the pin. Like I need the load on the pin before I can design the pin. That's what we're doing in here. So, all right. I think you're armed and dangerous. So I'm sure we'll all go home, do the homework, and come back with different numbers. Maybe not. Maybe we'll get the same number, but I doubt it. So it is. Did anyone look? Here, I can look. I can even do it technically cool here. Oh, maybe I can't. Oh yeah. Calendar. It is 9, 10, and 17. Let's just see if there's any tricks there. 9 is find the resultant. So you're going to be tempted to like do moments. The first 2 problems are not moments. It's just back to find the resultants of a concurrent force system. Okay. And then 9 and 10 are that way. And then 11 or 17. Yeah. 17 is one just like we did. It's going to have you find the moments of forces. You might not find them all. It might have you sum them, might not have you sum them. But yeah, so I think you're ready. Go for it. Huh? Yeah, 9, 10, 17. Yep. And then if you want to work ahead, 24 and 25 for Friday, but that's overachiever stuff. And I will put up another lecture. It'll be similar to this one. I'll probably throw in an angled force and go through the whole thing again. So you kind of get a feel for that. That's more complicated because that puts your resultant at an angle instead of vertical. That messes with your distance perpendicular. So anyway, I'll put that up.
It's the same textbook for when we take strength materials.
Yeah. Yeah. Bang for the buck.